Thank you very much for the kind introduction and for inviting me to this symposium. I have been working on biofiltration for almost 20 years, and I would like to show you some of the conclusions I say that I have after that 20 years related with which are the advantages, the drawbacks, and the opportunities and challenges that the biofiltration have nowadays. My talk will be divided in 3 parts. The first one is about biofiltration. It's a short overview about biofiltration. The second one is the biofiltration for the treatment of emission causing other nuisance. That is a topic nowadays, several countries, and there is a lot of countries that have new regulation and normatives related with the impact of the odor near the industrial installations. In Chile, for example, we have different sectors that has been regulated in terms of the impact of odor. And also, I think because of the problem of global warming, I think it's very important also to look at the biofiltration as a tool to decrease the emission, mainly related with those emissions generated in landfills or in wastewater treatment plants and in different agropecuarian activities that generate methane, but in very low concentration that are not valuable to get energy from them. So let's see which is a biofilter. Biofilter is a very simple technology. It's a very simple equipment in which you pass decontaminated air through a filter that is normally composed by an organic material or a mixture of organic material in which microbial communities are established to degrade all the compounds that goes into the contaminated air. Normally, that communities are present in the organic material used for the biofilters, or can be inoculated using aerobic sludge from wastewater treatment plant, or also we can inoculate from pure culture with specific abilities to degrade the contaminants that are in the emission. That is the strategy that we are using nowadays in the development that we have participated in at an industrial level. And of course, depending on the composition of the emission, we have the type of microorganism that have the abilities to degrade, oxidize the compounds present in the emission. If we have VOCs, so we will use chemoheterotrophic bacteria. If we have ammonia, for example, we have nitrification or anamox in the system to degrade or to oxidize the ammonia. And if we have sulfur compounds like sulfuric acid, that is one of the most treated gas by biofiltration, we use sulfur oxidizing bacteria. These microorganisms are forming a biofilm over the support, over the substrate that is used as a filter. Well, this is a scheme of a biofilter. Because of the capabilities of degradation are related with the bioreactions, then we need the microorganism active into the biofilter. So it's very important to keep at least the humidity of the system. So usually we have an humidification unit and the biofilter itself. Then the gas emission to be treated pass through the humidification, gets the moisture to allow to maintain the condition of humidity inside the biofilter.
I hope it works.
Thank you very much.
I hope it works here on the red one.
Okay, okay. And for this bed, we can use several organic material. We can use peat, compost, bagasse, wood chips, forest residues, pine bark, soil. And also, it is possible to use different organic material that have different, that gives different properties to the support. For example, zeolite, vermiculite, or perlite increase the water retention of the material, so the microbial activity could be maintained. Also, it uses shells in order to keep the pH into the system. As you can see, this is a system that is very difficult to control because it's not possible to control the temperature, for example. Microbial communities generate heat, and it's not possible to cool down the system just by the air or adding water with a sprinkler that is located in the upper side of the biofilter. This is how it looks, a biofilter, an open biofilter, an open bed, and this is a closed bed. As you can see, this is also in the atmospheric conditions. In winter or summer, there are different conditions in the operation of this equipment. This is avoid that different atmospheric conditions. And also, in this case, you can have the emission going downwards of the bed. The other biofilter is the biodrinking filter. That is a kind of a scrubber in which the biofilm is in the support material that is an inorganic material. In this case, there are some solutions that are circulated through the column to keep the pH or to keep some nutrients to the biofilm and to keep alive, to keep the activity of the biofilm. This is a more controlled reactor. You can control the pH, the temperature, and it looks like this. And these are the different support that you can use. Usually the same support that are used in a chemical scrubber are used in this equipment. And this is a figure in which we can see which are the applications of the different gas treatment technologies. Condensation, incineration, scrubbing, regenerative absorption, non-regenerative absorption. And if you can see here, there are the biofiltration, the trickling filters, the bioscrubbing that are cost effective when we have very low concentration of the contaminant and very high gas flow for treated. Then this is and in this part we find the problem associated with odors, for example. In terms of how to measure the performance of the equipment, well, it's possible to measure the thermal efficiency, just calculating the difference between the inlet and the outlet, the loading rate that is calculated, the concentration of the contaminant at the inlet, multiplied by the flow, divided by the volume of the biofilter, the elimination capacity, that is the difference between the outlet and the inlet, multiplied by the flow divided by the volume of the biofilters, and the empty bed receiving time, that is the volume of the bed of the biofilter divided by the flow. These are the main variables that we use to know how the equipment is operating. Well, there are many phenomena that occur inside of the biofilter. We have a biofilm, we have a liquid that usually is trickling through the system, we have the support, and we have the contaminated air circulated over the system. And this is the typical graph in which you can see the loading rate and the elimination capacity. This line corresponds to the 100% efficiency line. For example, if the loading rate is 1, well, here the elimination capacity is 1 also. We have then 100% efficiency. But if we increase the loading rate, this curve goes far from the 100 efficiency line, and it depends on the concentration of the pollutant and also the empty bed residence type that we use in the reactor. For example, we have here a biofilter with a biofilm of Thiobacillus thioparus for eliminating sulfuric acid in a biofilter with peat. You have the sulfur loading rate and the elimination capacity. Here you have the 100% efficiency, you see, 30 and 30, more or less. Here, with 25 works better. Here we have 100%, and then we have the other part of the curve. That means that the system is controlled by the activity of the biofilm, and here we have problem with the mass transfer. And that can be seen in these two figures, in which making some modeling and determining some parameters, we can see that in this part of the biofilter, in this part of this graph, we have a limitation by diffusion, and here we have a limitation by kinetics. In this graph, we also see that Acetobacillus thioxidans that have an optimal pH between 1.8 and 2.5 can grow or can remove sulfuric acid at high concentration in the inlet of the reactor. It supports very high concentrations. Here you have concentration almost at 6,000 ppm. That is a lot of sulfuric acid in the medium. For that reason, it is possible, for example, to retrofit some chemical scrubbers to convert in biodrinking filter. This is a work of David Gabriel and Mark de Heuses in a wastewater treatment plant in California, in which they convert this chemical scrubber in biodrinking filter, inoculating this kind of bacteria. And this is the result. This is the loading rate, and this is the elimination capacity. And you can see that the 100% line keeps till 100 grams per cubic meter per hour. This is the efficiency here. You can see the efficiency goes to almost 100% until this value. So this equipment can be used very efficiently to remove this contaminant in wastewater treatment. Also for ammonia, it's possible to find references of a very efficient system for removing ammonia. So we can see that the biofiltration is a robust technology when the emission contains one or a few compounds. Usually, it's used for treating odorous compounds like total reduced sulfur, sulfuric acid, dimethyl sulfur, and dimethyl disulfide. Also ammonia and trimethylamine as some VOCs. But when we have more complex emission causing odors, then usually the efficiency is not enough to avoid the impact of the odor nuisance of the installation. Due to the low odor threshold of some of the compounds present in these emissions. For example, here we have this biofilter that is located in the very south of Chile, in Paraguay, in la región de Yanquihue, that process the emissions from a fish feed production factory that belongs to a company that exports salmon. And the emission contain mainly organic acid, volatile fatty acid, and amines. And the efficiency in the removal of odor is from 97 to 99%. That, depending on the meteorological condition, some days is not enough to avoid the problem of odors outside the installation. And in Chile, you may know that Chile is a very long country. It's almost 4,000 kilometers long. The government have located different activities causing odor nuisance, more than 2,000 sites in 2013. Most of them located in the middle of the country where the population lives. Almost 50% of the population lives in this area, in the region of Valparaíso and the Metropolitana. And the main activities are related with animal, fish, and pet food factories, kraft pulp mills, pig farming, poultry and turkey farming, rendering plant, municipal wastewater treatment plant, and landfill. This has generated a lot of problems with the authorities that promotes the creation of normative and regulations. And unfortunately, in Chile, we don't have regulation in the land use in some areas. So it happens that this is a plant of an animal feed factory plant near Valparaíso. You see this is the situation in 2006, and this is the situation in 2017. And you see that there is a new development here just beside the plant. So these people is impacted by the odors of the plant. This is also a pig farm in 2006, and now this pig farm is very near to new population. The same happens with the wastewater treatment plant and many other industrial activities. But what about the odors? We can classify the odors in simple and complex. When we have a simple odor, we have just one compound. For example, sulfuric acid. That is easily recognizable, like the odor of a rotten egg. And all the odor substances have an odor threshold that is very low. For example, for all the reduced sulfur compounds, we have odor threshold in the order of part per billion, sorry. For example, hydrogen sulfide have 7 ppb of odor threshold. So our olfactive system is designed to have the possibility to smell the hydrogen sulfide in that concentration. And also, in all these TRS compounds, look at the butyl is almost 9 PBT. So these are very, very low concentration. So when these compounds are in an emission, it is necessary to remove almost 100% of that compound. Otherwise, it goes out of the system and generates an odor problem. The same for other compounds that we call it VOCs, like the propionaldehyde, and in the case of the reduced nitrogen compound, for example, the trimethylamine, that is the typical smell of the fish, is very low. It's 2 ppb. So this is a problem then when we want to treat an emission containing odors. But the problem is more complex when we have many gaseous compounds in an emission. And in this case, the only way to measure the concentration of the odor is by a method that is called dynamic olfactometry, that now is under a regulation on a standard, the EN 13725, that is the standard for the determination of odor concentration by the dynamic olfactometer in UE. This standard was also adopted in Chile, and now we have a normative for measuring the concentration of odor by the same methodology. And the methodology allows to measure the concentration in unit odor per cubic meter. And it's done by a panel selected because they have an odor threshold similar, all of them related with a substance that is N-butanol. And with this analysis, we can measure the concentration in the emission of the odor, and by modeling, we can see how, depending on the meteorological condition, we have an impact in some areas, and how will be the impact in the areas. So, biofilters treating odor emission then normally treat emission that contains more than 100 compounds. And just some of them are odorous, and usually also sulfuric acid and ammonia are present in high concentration. for example, in the case of a rendering plant. And in 2007, we were asked to find a solution for a rendering plant that is emitting a lot of odor and impacted an area of almost 20 kilometers around, almost a city, completely impacted by the odors of the plant. This was the situation. The city is here in this part. This is a plant that produces for processing turkey. They process 8 million turkey per year. 450,000 kilograms per day. It's a huge plant. This is mostly for export. Just 2 or 3% is in the Chilean market, and they have a rendering plant for producing feather flour, protein flour, and turkey oil. That's mainly used in pet food. Well, when we arrived, we made diagnostic of the situation, and the situation inside was really bad. The operators have always the doors open because they can support the concentration of the contaminant inside the place. And we made sure, the concentration, the mean concentration during the day, and we found that the H2S goes from 50 to 500 ppm in a day, and in ammonia from 500 to 5,000 ppm in a day, with a mean flow of 540 cubic meters per hour, and with a temperature of 30, more or less 5 degrees. And with a lot of organic acid that we couldn't recognize all of them, but with a variable concentration from 1,000 to 10,000 ppm. And we designed a solution. The solution, because of the concentration of sulfuric acid and ammonia, was to install 2 chemical scrubbers to decrease the concentration of the ammonia and sulfuric acid, and then a biofilter. This, we call it BAOS Críticos, that come directly from the equipment that produce the emission, the more concentrated emission. And the BAOS Frios is the emission that we collect inside the building. We install a pneumatic system to extract all the emission inside the building to bring to the plant. And here we have the humidification. Well, this is the first scrubber that works with sulfuric acid for decrease the amount of ammonia. This is a scrubber for the sulfuric acid that works with NaOH and Na with sodium chloride. And we have the humidification and the biofilter. Unfortunately, the company accepted the solution. I was very surprised, really surprised. And they hired an engineering company to make all the details, engineering details, and the construction. And while I was here in France, in Alès, they were building the plant. This is the plant. This is the first scrubber. This is the second scrubber. This is the line that comes from the building with the coal emissions. And this is the humidification system. And behind is the biofilter that have a chimney also, just in case we have some odors after the treatment, just to dilute the odors. They don't have many confidence in the system at that time. And here you have the biofilter that have a roof, and this is the chimney. And you have here, I don't know, probably you can see, but this is the inlet to the biofilter, in which here is the concentration of sulfuric acid, that is 7 ppm, ammonia is 15, and the VOC is about 3,300 units. And here you have the outlet over the surface of the biofilter, and you can see that it's 0 in VOCs and 0 in ammonia and sulfuric acid. It goes very well. It has an efficiency of 100% most of the time. So that allows a solution in which the impact of the odor that was almost 20 kilometers around and just a few meters around the plant. And with concentrations that are allowed by the regulators. But what happened in other industries? For example, in the pig industry. Usually, the odor is less than 70%. Usually, the biofilters there are reported with efficiency lower than 80%. And which is the reason for that? The reason is because when we have an emission with 100 of compounds, the characteristic of these compounds are very different. And what's important here, this characteristic or these values, the Henry constant, the solubility, but most important is the log-K parameter that shows the ability of the chemical compound to form H-bond with water. That means that the compound is more or less hydrophobic and can be bioavailable for the microorganism to be degraded. And in a pig producing facility, swine producing facility, we have a lot of compounds coming from the protein, that is the more nasty compounds in terms of odors, that is aromatic compounds like the indole, the paracresol, that have very high low-K value. That means that these compounds are very hydrophobic. So when we have a biofilter that works with humidity, that there is a lot of water there, then these compounds pass through the system. So this is a very complicated problem because depending on the empty bed residence time, the profiles of the concentration inside the biofilter are different. For example, this is the height of the column, and this is the concentration of the contaminant. Here, this is the concentration in the inlet, and the contaminant is consumed along the column and goes out in a concentration that can be 0, in this case, or not 0. So these profiles can lead to an stratification of the communities that we have inside the biofilter. For example, if we put an inoculum in the system, the community's growth, we feed with the emission, and the emission generates some stratification that generate a profile of the different compounds along the biofilter. And some of them can be completely degraded, and some of them are going to not to be completely degraded and goes out of the biofilter. And there are a lot of interactions in the microbial communities inside that makes the problem a bit more complex. Well, we set up an experimental system to see this, what happened in the biofilter. This is the column with this is a bioticking filter with different systems to feed the different contaminants into the system. And the mixture of gases was sulfuric acid, ammonia, methanol, dimethyl sulfur, 2.5 dimethylpyrazine, and we inoculate the biofilter with Thiobacillus thioparus, Aminobacter aminoborans, Methylobacterium organophyllum, Nitrosomonas europea, and Rhodococcus erythropus. All these microorganisms have abilities to consume or degrade these compounds. Well, we measure all the system, all the compounds by different methodologies, by gas chromatography mainly. And we also set up all the methodologies for measuring the different genus present in the biofilter by qPCR. We follow the biofilter for almost 2 years. This is the H2S concentration. As you can see, this is the efficiency, 100% always, 100% in the case of the ammonia. This is the removal efficiency. This is the inlet, and this is the outlet, always 0. And this is the elimination capacity. The same for the other gases. And this is for methanol and for trimethylamine that were fed afterwards. For example, trimethylamine, we began the feed in the day 200. And it affects, the addition of trimethylamine affects the removal of methanol here. You see, this is the day 200, and because of that, the efficiency of methanol was down. In terms of the profiles, this is the profiles of the compounds along the column. This is at day 250, and you can see that sulfuric acid and ammonia are consumed in the very lower part of the biofilter, and the other compounds were removed in other parts. This is the situation in day 538. You can see that ammonia and sulfuric acid are consumed in the lower part, and the other are consumed in the middle part, but after that they are not consumed and goes out of the column. in terms of the relative abundance of the microorganisms that we inoculate, you see here the situation at day 250, this is the day 338, and this is the day 538. And in the colors, you can see the different microorganisms and genus of the and what happened with them. For example, at the beginning, Thiobacillus thioparus was distributed all along the biofilter, but at the end, the main concentration was in the lower part. But what's important of this figure is that the biofilter was alive in terms of there was changes in the community in the time. So that means that the biofilter is working according how the communities are changing inside. So it's very difficult to predict what happened in the biofilter in terms of the different compounds that can be removed. And that is a conclusion for that part due to the different nature of the chemical compounds and the dynamic that we have of the microbial communities inside the biofilter. It's very difficult to predict the performance of in the time of a biofilter for treating emission causing or other nuisance. And this is very important for the people that buy one of these equipment, because these people want to have an equipment that works always 100%. And it's very difficult to certify that situation. So I had a lot of agreement with the people that try to sell these technologies, promising that it was very well for a long time, but it was possible to be sure. So more research have to be done considering the oil concentration as a variable operation. But usually, and it's very difficult to find in literature, the performance of the biofilter in terms of other units that is necessary in these cases. Well, the third part of this presentation is about bioxidation of methane from landfill. Particularly the elimination of methane from old or abandoned landfill. Almost 50% of the methane that is produced in a landfill is liberated as a diffusive emission into the atmosphere. And nowadays, there are some people that say that we worry more with the methane than the CO2. We can have a better result in terms of decrease the slope of the temperature increase that is generating these problems with the climate change. And it's a low-cost technology, and it's just using biofilters inoculated with methanotrophic bacteria. Yeah? Methanotrophic bacteria is an ubiquitous bacteria we can find everywhere, and this can be a key technology for reducing methane emission as greenhouse gas. In a landfill, there are different sectors in which this diffusive emission could occur. And it's not easy to measure these emissions, but just a few months ago, a plane of the NASA that have an instrument to measure emissions from the air took a picture of all the landfill in Chile. It was in January, just in January. And you have some pictures. This is from 11th of January 23. This is 13, 14, 13, 31. My birthday. And here you see the emissions of methane from the landfill. And they can estimate the emission. The emission in that landfill is about 673 kilograms per hour. In Chile, there are more than 300 landfills. So we can multiply this amount for that numbers. And also, they take a picture of the La Farfana, the biggest wastewater treatment plant of Santiago. And you can see that in the sector where the anaerobic digestion there are a lot of methane. They estimate 270 kilograms per hour emission of methane from the system. So the diffusive emissions are really a problem that have to be solved in all these operations. And there are some people working on this. These are two brilliant scientists that have been working on this for a long time. And they propose bio-windows, bio-covers, and biofilters to solve this. These bio-covers and these biofilters are just put the material in order to guide the landfill gas through a system in which the methanotrophic bacteria could oxidize the methane. The same with the biocover, that is just put in the different cover that put in the landfill to protect the system. But the idea is to develop a biofilter that can do that. And we can have everywhere a biotreatment filter, ideally, to control better the conditions. So we did some isolation of methanotrophic bacteria from the landfill cover. We isolate these bacteria. These bacteria have a typical pink color, and we grow in a reactor. And we inoculate different biofilters, and we studied the effect of the inoculum on the biooxidation. That means that we did bio-augmentation, and it's worked very well. But still, there are plenty to do in this subject. For example, to improve the mass transfer of methane in biofilters due to its low solubility, to understand the behavior of methanotrophic communities in the dynamics of biofilters, and to study the effect of the other gaseous compound present in the diffusive emissions, because when you have a landfill, you don't have only methane. You have sulfuric acid, you have ammonia. And we are working on that nowadays. So this is my presentation. Thank you very much for your attention. And I hope to have some questions.